But if I have a false in here anywhere, I'm gonna have a false statement. But if they're both true, it's true. If there's a false anywhere, it's false. So finally, if we take this big bracketed thing, we start here and we end with Q, right? Start true, end true, that's true. Starting false, it can't be anything other than true. So I'm just gonna take a peek at, well, what's this one? Start true, end true, it's true. All right, so this one is all truths, it's gonna be valid. Well, you could probably guess from what this argument was saying that no matter what was gonna happen, it followed that the person was just gonna be miserable. He's miserable if he tells you, miserable if he doesn't tell you, so he's just always miserable. Valid argument. So that's kind of our warm-up here. Let's jump over. Let's jump over to some of these other things. What if we look at something like number 38? Still has a conditional statement in it. If I watch Schindler's List and Milk, I'm aware of the destructive nature of intolerance. Okay. But think about, what does this say? Symbolically. I watch Schindler's List and Milk. Well, that might be my first statement, but maybe I ought to, before I go any farther, let me look at the rest of this. Today I did not watch Schindler's List, or I did not watch Milk. Ooh, they separate those. I think I'm gonna think about separating these up here as well. Therefore, today I am not aware of the destructive nature of intolerance. Wow. Okay. So let's split this up. If I watch both of these, maybe I could put it this way. If I watch, take the if out. I really have two little statements I'm putting together. I watch Schindler's List would be one statement. I watch Milk would be a second statement. And the third statement that I see buried in here is, I'm aware of the destructive nature of intolerance. So, if we think about it as three little statements, here are my little statements that I'm working with. And I'm just putting them in here on here's the first thing I read. I watched Schindler's List. So there's my P. This is a sneaky thing. There's an and in here. But later on, we can see in the second premise that they've separated watching these two movies. So I think it's a good idea for us to say that our second statement, statement Q, is I watch Milk. And the third statement that they seem to have in here is this, I'm aware of the destructive nature of intolerance. So I'm aware of, etc. Okay, I'm not gonna write that whole thing. So if we agree, here's what our little statements are that are involved in this argument, then let's do some translating. If I watch both of these movies, that would be P and Q, right? So if I watch both of these, that would be a conditional statement. So if P and Q, then I'm aware of this stuff, all right? So P and Q, arrow R. There's the first premise. It said, today I did not watch Schindler's List, so not P, or I did not watch Milk. There would be not Q. And that's it on our premises. So the conclusion here is, today I am not aware of the destructive nature of intolerance. R is I am aware, so this would be I'm not aware. So again, we want to put these together. So take your first premise, add the second premise. Notice I'm using parentheses around the two separate premises, but once I've added them together, I'm putting my big brackets here. These should lead us to our conclusion. Good news is, this isn't a very, very, very long argument, but bad news is there are 3 letters involved. So when I have 3 letters, I'm going to have a column for each letter. But again, I've got to get my premises into my table. And again, just so I'm aware of this, I have 1, 2, 3, 4, 5, 6, 7, 8 logical symbols. So I've got 8 more columns to put into my table. I need to have one for P and Q, so that I can find P and Q, arrow R. Right. Then I need to have the second premise, but for the second premise I need to have not P. I need to have not Q, and then not P or not Q. Right. So now I can put those all together. Right. How am I putting them all together? I'm saying, well, P and Q, arrow R, and not P or not Q. I can see I'm going to have a spacing issue here. Let's put big brackets around this because I really, really need my big brackets now. I'm all ready to put my conclusion in here. My conclusion is not R. I don't have that in my table, so I better put not R so that I can have, finally, my big brackets, arrow, not R. I need that so that I can squeeze this into my table. But I've got 3 letters, which means I'm going to have 8 rows in my table. It is always 2 to the number of different letters. So I need 4 T's and 4 F's. I always have half true, half false. So the first letter is always top half true, bottom half false. The second letter is always going to take however many truths you had, it's going to cut that in half. Well, half of 4 would be 2. And alternate from there. So we're going to have true, 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 false, false, true, true, false, false. The last letter is always going to be just alternating back and forth, true, false, all the way down. So every table starts off the same way, kind of a pain. Conjunction is only true when both statements are true. And notice in our table, top 2 rows, the P and Q are both true. But all of the rest of the time, something is false. So I've got 2 trues and then 6 falses. So now I have a conditional statement. Conditional is only false if I start true and end false. So if I start true, end true, it's true. But the second row, it's false. All of the rest of this, I'm starting false, which means it cannot be anything other than true. I'm going to have 6 T's. So 1, 2, 3, 4, 5, 6 T's. So I need not P. Not P would be the opposite of P. P was 4 trues and then 4 falses. So this is going to be the opposite, is 4 falses and 4 trues. Q alternated. We're going to alternate this one. False, false, true, true, false, false, true, true. The OR statement is only false if both statements are false. That does happen in the first 2 rows here. Both statements are false. That's going to make this false. But as long as there's something true, we're going to have a true statement. So I've got 6 T's here. So now I've got to put together my 2 premises. Here's the first premise. Here's the second premise. We're adding them together with a conjunction. The only time a conjunction is true is if both statements are true. So if I see, oh, I've got a couple of falses here, that's automatically going to be false. And if I look at the bottom 6 rows, everything else is true, true. So that's going to be 6 trues. Not R is the opposite of what it will have for R. R is alternating true, false, true, false. This is going to be false, true, false, true, false, true, false, true. So now I have a conditional. And this one, lucky for us, it actually reads left to right for once. The conditional statement is only false if we start true and end false. If we start with a false statement, it will automatically be true. But if we start true and end false, that would be false. All right? And if we start true and end true, it's true. Start true, end false, it's false. Notice this is alternating. This is all starting true. This is alternating. So I have false, true, false, true, false, true. So here is my truth value. This particular argument is so full of holes. It's just not occasionally not coming out true. It's like not coming out true almost half the time. This is invalid. Now, it would be really neat if we didn't have to go through this process every single time. Maybe we could see that there's a little bit of a pattern one that is always going to work. I can't necessarily tell you that you won't have to do some translating, but take a look. I'm gonna back up a couple of pages in the textbook here. Because I want you to see aha, I found what I'm looking for. This is table 318 in the text. Grab this and slide it over just a little bit. There are some kind of common statements that are always true, or that common arguments, I should say, that are always true or valid, always valid. So if you look at the top row of arguments, these always work. These are always going to be true. So if we start P, end with Q, if P then Q, in our other premises we have P, therefore Q. This is called direct reasoning. Contrapositive reasoning says if P then Q, this is our conditional statement. Well, we don't have Q, therefore we don't have P. This is kind of like saying, remember, a contrapositive statement and the original conditional statement, they are logically equivalent. So I don't have to have my conditional statement and say, yes, I've got this same antecedent, therefore it makes sense to have the same consequent. I don't have to have that. I can kind of turn it around. If I know this premise, I know I have this premise, and I can maybe turn it around a little bit into an if not Q, then not P kind of situation. That would be contrapositive reasoning. Disjunctive reasoning, the argument says, I've got this or I've got that. I don't have one of them, so I must have the other one. Right? So, don't have P, therefore I must have Q. I've got this or I've got this. I don't have this one, so I must have this one. I don't have Q, therefore I have P. This is disjunctive reasoning. Transitive reasoning is kind of a chain of thought. If P then Q, Q leads me to R. So basically, if I start with P, I'm going to end with R. That's the conclusion. Transitive reasoning. All of these work. They're always valid. There are some situations that are always invalid. People make these kinds of mistakes in reasoning all the time. If P then Q, I've got Q, therefore I must have had P. No, doesn't work. If P then Q, not P, therefore not Q. What we're kind of looking at is those different versions of a conditional, the conditional statement, the different ways we could turn it around. We had a converse, we had the inverse, we had the contrapositive. You can't turn things around and have an equivalent statement, is essentially what they're saying here. The fallacy is a common name for a badly logicked out argument. It's a fallacy. Misuse of disjunctive reasoning. Okay, notice how this is similar, but not quite the same as the valid argument. There's a negation in here, you gotta be kind of careful. Misuse of transitive reasoning. This is saying if P then Q, if Q then R. Now if this was correct, we would say if P then R. Start with P, we'll end up at R. This has it turned around. This is backwards. So it's just a rule that's been misused. When you take your test over chapter 3, I know there's a lot of stuff to remember in here. And I don't know if you're gonna like this table or not, but I would be totally cool with your copying out whatever little factoids that you want and putting it on, like I'm putting my hands out here, but like on a 3x5 note card. All right, anything you want. So it could be any of those basic truth tables. It could be like these kinds of reasoning. It could be De Morgan's laws, or how do I write the converse, inverse, contrapositive. All of those would be good things. But what I wanted to show you here is, we can jump back to the end of that section again. Wouldn't it be kind of cool if I could look at some of these problems and just save a little bit of time by being able to say, look at number 27, for example. If I'm tired, I'm edgy. If I'm edgy, I'm nasty. Therefore, if I'm tired, I'm nasty. Notice the kind of chain of thought here. You start here, you go to edgy, and from edgy, you go to nasty. So it seems like you start with the tired, you kind of go through this chain, and you end up at nasty. Look at this. If I'm tired, I'm nasty. That's that transitive thought. Right. So I could say, hey, this is going to be valid because this is a transitive argument. It was on that list of arguments that always work. Well, I just saved myself a whole lot of time, because think about this. There are 3 different little statements in here, so that would be one of those 3-letter tables with 8 rows in it. If I don't have to do that, I'm pretty happy. But by the same token, I can save time on this one. Look at number 29. If I'm tired, I'm edgy. If I'm edgy, I'm nasty. This is kind of transitive thinking should lead me to, if I'm tired, then I'm nasty. But look at their conclusion. They flipped it. They start with nasty and end up with tired. That's not going to work. So this one would be invalid. Okay, and again, because it's misused the transitive. So if I say something, here's why it doesn't work. They've screwed it up, man. It's not working here. So again, some of these little shortcuts, if you can identify, I've got this shortcut. We don't always have to have the table. Right? So that's the good news. So what do you think of these arguments so far?
Interesting.
The one thing that has been true up to this point with these arguments is in every case, it's been translatable into our logical symbols so that we could actually put it in our truth table. So I've always had statements that were translatable. What if I don't? What if I don't have a translatable argument? That would be the next thing. The only kind of statements that we had that we could not translate easily into conjunctions and disjunctions and conditionals and biconditionals. The ones that we couldn't do that as easily, and I'm gonna say, or at all, we haven't talked about translating some of these at all. That would be those, what did we call them again? The ones with the some, the no, the all. The quantitative statements. What in the heck do we do when we encounter a quantitative statement? I'm going to jump over to problems that are at the end of section 3.8. And there aren't very many of these problems, actually, but notice what we've got in these. We've got those quantitative statements, and yet we still have arguments. In order to figure out, hey, do we have a valid argument when we're dealing with these quantitative statements, we're going to use what's called an Euler diagram. Okay. Euler diagram actually starts with an E, but we pronounce it Oi. So Euler diagram. Euler diagrams take our three basic quantitative statements and they draw them this way. If I wanted to draw a picture of all A's are B's, if I wanted to draw a picture of this, I'm going to draw two circles, one inside the other, and the A circle is going to be inside the B circle. What this is saying is all of these A's, all of these things that are in this A circle are inside my B circle. This is almost going back to our Venn diagrams. Okay. Kind of, sort of. But there's no universal set, there's nothing like that here. I also want to show no A's are B's. Now the easiest way to show no A's are B's would be to say, well, here's my A circle and here's my B circle. They don't overlap at all. None of these are over here. But the third basic picture I have would be some A's are B's. Now when I say some A's are B's, I have this kind of thing. I've got a little bit of overlap. So if these are my A's and these are my B's, I could say you know, there's something, I'll put a little X in here, there's a little something in here that is an A, but it's also a B. So some A's are B's.
Hmm.
Right. These are my three basic Euler diagrams. Now, I can start putting other stuff in here as well. If this is some A's are B's, here's another picture. What if I said some A's are not B's? Okay. Some A's are not B's might look a little bit more like this. Still have the overlap. But what if I said there's some A over here that's not a B? Right? So I'm just indicating there's something. I'm not shading an entire region like I would have with a Venn diagram, because all I'm allowing is there's just something out here in the A circle that's not in the B circle. Now here's the deal. When we're thinking about these Euler diagrams, what we're going to do is we're going to try to use Euler diagrams to picture our argument. Right? So our procedure is going to be this. So this would be